we do it the same way as we calculated the torque resultant, right? We look at our cross-section. That's our cross-section again. Same old cross-section. This is my x-axis. This is my z-axis. And this is my y-axis. Okay? So if I consider all these stresses coming out this way, coming in this way, let's take a little sliver at the bottom and a little sliver at the top, corresponding wise. So I take a little sliver here, little tiny sliver of height dy, and then at the same distance from the neutral axis, I take another sliver. This geometry is horrendous. Okay, at the same distance from the neutral axis, which is this line here, I take another sliver at the same distance. So these two slivers of surface, they are at the same distance from the neutral axis. They say that this is y, then this one is minus y. You see? Okay, so on this guy, I'm going to have all tensile stresses. So there is going to be a force resultant from all these tensile stresses. Let's call it dF. That's going to be coming out. You see? On the top, I'm going to have a force resultant from the compressive stresses, which is going to be going in. You see? So I look at the cross-section. I take a sliver of the cross-section at y and minus y, so these two are symmetric with respect to the neutral axis. I'm going to have tensile stresses this way, compressive stresses this way. And because the distribution is symmetric, the magnitude of these two forces, will it be different from each other or the same? It's going to be exactly the same. So these two guys give me a force couple. This is the whole thing about the fact that the resultant axial force is 0, right? Because I can do this at every position. I can do this, is going to have its match right here. And this one is match here. And this one is match here. Each sliver has its match. Each of them are force couple. There is no net axial force resultant coming from these guys. But they give me what? What do these force couple give me? You see, it give me a torque. It gives me a torque. There is a little bending moment resultant, a little differential bending moment resultant. If this area here is dA, there is a little bending moment resultant, which is equal to the forces dF times the distance. And the distance is 2 times the radius. 2 times y. So these two forces are a force couple of magnitude dF, and the arm of the couple is 2 times y, because this is just y, this is minus y, distance is 2y. Right?
From each other?
From each other. When you do the moment resultant from a force couple, you get the magnitude of the force times the distance between the two forces. Okay. What is this force? So this force, if I do this force here, remember down here, minus cancels out. So that force here, if I use the expression over here, is going to be E that multiplies y over rho. And this one multiplies the 2y. And this one is the stress. So I still need to put an area in there times dA, because this is the stress over the whole area. dA times 2y. Fantastic! I'm almost there. I'm almost there, because then I can continue doing that. I do this lever and the friend, this lever and the friend, this lever and the friend. And I keep summing up. Say that I walk from minus h over 2. If I sum them all up and I go from minus h over 2 to 0, because remember, I take this, I take this. I take the next one, I take the corresponding one. So as I walk my way up to the middle, I'm taking all the couples. So my whole moment is going to be from minus h over 2 to 0 of 2 times e y over rho, and I have a y squared dA. Well, instead of doing minus h to 0 with a 2 factor, because everything is symmetric, I can simply do from minus h, so from minus h over 2 to h without the 2, which really means I'm integrating over the area. So this becomes the integral over the area of e y squared over rho in dA. Kaboom! Yes?
How do we get dF to be EY over rho?
dF is equal to the stress times the area. The stress at distance y is E times minus y over rho. This force here, positive coming out, is a minus y. Boom, I get that one.
So that's for the minus y one?
Yeah, remember this is a force couple, so I'm getting the magnitude of the force times the arm, and because I'm looking at the resultant coming at me, the signs work out that way. Okay? So if you have a positive curvature, think about it in another way. See, this relationship here is really a relationship between the bending moment and the curvature now. So you see that the signs work out right. So the next step really, I'm done. I have moment this way. I have curvature inside. This is the time that the rabbit comes out of the hat again. She's like the same rabbit. Because now what I pull out of the hat is the 1 over rho. And man, I'm done. Because now I have my moment is equal to 1 over rho times the integral over the area of E times y squared dA. See this? This is, I don't even know how many stars I want to put there. A gazillion stars. Okay, this is like the whole Milky Way of stars. This is the relationship between the moment, the internal resultant, and the deformation, which is the curvature. It is connected, the two are connected through something which has to do with the property. This is, guess what we're going to do? Remember EA effective, GIP effective? Material, geometry. This is going to be our effective section stiffness, right? So if E is homogeneous, if 1E, so if E is constant, because that's what we're doing today, we're going to do the whole story on next class, but constant too many. So if E is constant, then I can take it out, and I get that this one is equal, I get that the moment is equal to 1 over rho times E times the integral over A of y squared dA. This is just a geometric property of the area. That one.
Where y squared again is the distance from the center?
Yes. So this tells you to calculate this property of the area, go over your whole area, look at all the little dA that you have, and sum up how big they are and how far they are from the neutral axis squared. This is called the moment of inertia of the cross-section. We did polar moment of inertia because we were summing r squared dA. In bending, I don't care how far I am from the center of the beam. I don't care about r. I don't care about the radial distance of spots. I'm only interested in how far I am from Switzerland, right? How far I am from the neutral axis. That's what matters. That tells me how much is my strain. How much is my stress? How much is my everything? So the properties of the cross-sectional area that matters in bending are only the cross-section, not P, boom, P goes, P polar goes with R. I is the moment of inertia of the section, moment of inertia. You calculated these kind of things in your calculus classes, right? You did all kind of this integral, or when you do dynamics. So this is really geometry. So if you take a cross-sectional beam that is a rectangle, if I take a cross-sectional that is a rectangle like this, and this is H, as we were saying, and this is B, if I do, and if I take the y at the middle of the cross-section, so this is symmetric, and if I go the integral over the area of y squared dA, I find that this is equal to b h cubed over 12. Given b and given h, that's done. It's calculated once and for all. You can do the integral if you want, if you don't trust me. Or if you have a round cross-section of radius r, right? And if I do the same integral, in this case, I get that the moment of inertia of the cross-section with respect to an axis, so if this is your y, and y equals 0 at the diameter of the cross-section, you find that this I is pi r to the 4th over 4, not over 2, over 4. And actually, doing this integral is kind of a pain in the neck. The easiest way to do this integral of y squared dA is to imagine that your r squared dA is x squared plus y squared. They're both the same, so each of them is half of the r squared dA, if you want to save your integration skills for something more worthy. Okay? So these i's, what I'm saying to you is that these i's are geometry. Either you calculate them, if you really want to see where they come from, or we give them to you. We're going to do more complicated cross-section on Tuesday. But for now, for what you have to do now, you only need to know that the moment of inertia of a rectangle is bh cubed over 12, of a round cross-section is pi r to the 4th over 4. Notice that the units are the same units as your IP, right? These are meter to the 4th, line to the 4th are the units for I. Okay, so this whole thing, this whole relationship, I can then write it as my final destination for today, which is how you solve all your problems in the problem set that is going to be assigned to you, is then that the moment, so if I invert that one, I find that the curvature is equal to m divided by EI of the cross-section. Sounds familiar? 1 over rho, which we see is going to be our d theta dx. I can tell you already that that's where we are going, right? Remember, the u dx is n over EA. d phi dx is t over GIP. 1 over rho, which is going to be d theta dx. I can just already break the news to you now and give you a spoiler, is m over EI. Okay? What does that mean? It means if I give you the moment, you can get the curvature. If you get the curvature, you get the strain. If you get the strain, you get the stresses. Same path as always, just different characters. And one thing that I can tell you is that although everything that we did today was thinking that we had a beam at constant curvature, when we derived this relationship, at the point we were looking at one section, right? So this relationship here, if I have a moment which is a function of x, then they still work. Like a homogeneous beam in which I have a moment that's a function of x, I have at position x a curvature which is moment of x divided by EI. EI can also be a function of x. But this relationship here, the same as we were doing in axial loading and torsion and so on, if you have the resultant inside, you can find the deformation at that section by dividing the resultant through the stiffness of the section. Nothing new. It's the same thing. You must be bored to tears. I am sorry, but it's the same thing. But it's good. The repetition is good because bending gets a little more tricky. Where it gets tricky is right here. Who is giving you this M of x? Where does it come from, right? So this is where it gets a little more tricky. So let me tell you 10 minutes to get started on how we get this M of x in things that are not as simple as I come to you and tell you, I give M0 to the end, and you're like, well, the M is M0 everywhere, right? Things get more messy than that. So let me clean this mess, and let's figure out how we get M of x. But if I have M of x, and if I have 1 over rho of x, out of this, chalk's gone. Remember that once I have 1 over rho of x, I can calculate the strain as minus y over rho, and this now is a function of x. So the strain, if you have a beam where you have different curvature at different cross-section, and if I look at a certain cross-section, which is at x, and if I want to know the strain at every point on that cross-section, at every point, I'm going to have a strain which depends on how far I am from the neutral axis, y, but it also depends on the curvature at that section. So the strain is a strain of x and y, right? You see what I mean? And this curvature, 1 over rho of x, comes from this. So this becomes equal to minus y m of x over EI, and in general, this can also be a function of x, the same way as we were doing torsion. You see how amazingly similar it looks to torsion? In torsion, we had the gamma, it was R times T over GIP. They're all very symmetric, so I'm going to give you some tables that show you all the connections, all the way they look the same, just with different characters. Okay, so just what we did today, if I give you moment of x, you can get curvature as a function of x, you can get strain as a function of x and y, you can get stress as a function of x and y, you can get everything inside a beam right now. The only little missing step is, what is this guy?